differential operator, so the derivative of respect to n minus 1 to the log of the partial function, and taking n goes to 1 limit, you get the entanglement entropy. Okay, but in principle, if you know this guy, then everything is okay. But the computation of Zn is very non-trivial. But okay, but I will list several properties of the entanglement entropy in quantum field theory. Okay, so as I have briefly mentioned, so entanglement entropy has UV divergence. UV divergence. So in d-dimensional quantum field theory, entanglement entropy has a divergence proportion to 1 over epsilon to the d minus 2. So this is UV cutoff. This is UV cutoff. And you have subleading divergences. D to the d minus 4 and dot dot dot. And depending on the dimensionality, you have log divergence, C naught, for even D. So when the dimension is even, you have log divergence. On the other hand, you don't have any log divergence in odd dimension. And this is finite. Yeah. Actually, there is a finite part in even dimension, but it is not universal because you can shift the value of the constant part by scaling epsilon. Okay. And this the first coefficient is proportional to the area. This is proportional to the area of the entanglement surface. This is called the area rho. Area rho. And C naught is related to the conformal anomaly in even dimensions. So in even dimensions of the C, when D is even, there is a conformal anomaly in the theory. Conformal anomaly. And C naught is related to the central charge. Central charge. Yeah, I will discuss it in a moment. And on the other hand, in odd dimension, there is no conformal anomaly, but you have a constant part, gamma. Gamma is called topological entanglement entropy. Topological entanglement entropy. And gamma is supposed to be positive. And this is a nice order parameter for topological phases in condensed matter physics. And for us, it is also very important because this gamma is related to the partial function on a sphere, as we will see later, maybe in Friday. So this part becomes very important.
Do you implicitly assume that quantum coefficients are taken into account up to one loop?
Yeah, this is quantum partial function.
Up to one loop?
For green theory, it is at the one loop level. But in general, it is at all order.
So, for example, 2 loop, 3 loop, question are also taken into account?
Yes. You have to take into account everything. Yes.
Is this only true for CFP or general
this part? This part or
no for those general?
this is very general. This is general form. So for massive case, okay, for example, if you have mass gap, then C naught also depends on the gap scale. Not only depends on the central charge, but also depends on the mass gap. Okay, and gamma is also depends on mass gap. Okay, so I will focus on the conformal field theory from now on. Okay, is there any questions? Okay. In last 20 minutes, I will focus on conformal field theories, and I'd like to explain why C naught is related to the conformal anomaly. Okay, so I have a system A whose typical length is given by L, small l, and I consider the scaling of the partial function or the system. So I'm interested in the scaling of the partial function, but on the singular space. So this is Zn, and I have log of Zn, and I rescale the system. So this is the scaling operator. And scaling is equal to, okay, I have d-dimensional CFT. And this is equal to acting a differential operator made of the metric. Okay. So these are equality. Okay. These are equal. So rescaling L is equal to changing the metric. But this part is equal to minus, in my convention, this is a trace of the stress tensor. This is stress tensor of my system, and my definition of the stress tensor is in this way. So then, by using this relation, then the rescaling of entanglement entropy, if you remind the definition of the entropy, then you see that you have you act this differential operator, and sorry, then the entropy. So the rescaling of the entropy is given by this guy. So the expectation value of the stress tensor P mu mu. And if there is, yeah, okay, if this is 0, then you don't have anything, so it equal to 0. But in some case, this becomes non-zero. I will denote this guy as a C naught of sigma. And you see that then, so I'm computing the rescaling, but this is nothing but the derivative with respect to log of L. So if C naught does not vanish, then you have a log divergence. Okay. So which means that if you have C naught, then you have a log divergence. C naught times log of L. But you have to make it dimensionless. So I introduce UV cutoff here. Okay. So this guy is the origin of the log divergence. Okay. for conformal field theory, this guy is always 0 at the classical level, but quantum mechanically this does not vanish because of the conformal anomaly. And conformal anomaly only appears in D dimension, sorry, in even dimension. So in odd dimension we don't have any log divergence, but in even dimension we have a log divergence due to the anomaly. So in even dimension, so the stress tensor is known to have anomaly, and in my notation I have A anomaly minus the others. So here, so ED is the Euler density. This is Euler density. Euler density. So this is a polynomial of the Riemann tensors. Okay, and these are also some polynomial made of Riemann tensors. It is called wire invariant. And A and B are the central church. These are central churches. Central church. Okay. And in two dimensions, there is only one Euler density. Okay, Euler density is always only one. Okay, I mean, there is one Euler density in even dimension, in any dimensions, but there are several wire invariants in higher dimensions. But in two dimensions, we don't have any wire invariants. In two dimensions, we have only Euler density. So the stress tensor is given by C times R. And yeah, I will rewrite A as a C here, and R. So E2 is 1 over 4 pi times R. R is rich scalar. This is rich scalar in two dimension. So this is conformal anomaly in two dimension. So here, so we see that C naught is equal to C third in two dimension. So if you have, if you compute the entanglement entropy in two dimension for an interval, so this is my region A. So since the spatial dimension is 1, so we only have an interval as a region, and whose length is L. So in two dimensions, the entanglement entropy of an interval is given by C third times log of L divided by epsilon. So this is the entanglement entropy in two dimensions. So two-dimensional CFT. But in four dimensions, we have two terms, two anomalies. In four dimensions, we have one Euler density, E4, and one wire invariant. So this is something like R squared plus R mu nu squared plus R mu nu rho sigma squared with some coefficients. Okay. In this case, so you can compute C naught, and it is given by minus 2A times the Euler number for the entangling surface. Okay, here Okay, originally we have a Euler density for the four-dimensional space, four-dimensional manifold, but here, after the computation, so you see that okay, this is the Euler number for the entangling surface, sigma. This is two-dimensional. So this is two-dimensional surface. Sigma is now two-dimensional surface, so which divides your system into two parts, A and B. Okay. And this is the Euler number of sigma. This is Euler number. And so from this term, so you get some integral over sigma. This is two-dimensional integral of some function of the eccentric curvature. So here we have eccentric curvatures. K. I will not write in explicit, but here you have some polynomial for the eccentric curvatures. Eccentric curvature means that you have sigma, and you measure this curvature from outside. You have some normal vector and also some vectors. You can compute the curvature for sigma. Okay. So this K is extrinsic curvature. Extrinsic curvature. Okay, anyway, you can compute the coefficient in four dimensions also. And so you see that the C naught is always given by the center charges. So in four dimensions we have two terms, C and A and C. And so whose coefficients are given by geometrically. Okay, so this is a geometric invariance for sigma here. You have Euler density here, Euler number. Okay, so next, so let's see that what happens in odd dimension. In odd dimension, there is no conformal anomaly. So we don't have any log divergence. But once we focus on a special shape for the entangling surface, okay, let's consider a spherical entangling surface. So now sigma is just a sphere, D minus two-dimensional sphere. So I focus on this case. Then I have time, and but this is actually the Euclidean time. And you have spatial slice, and I take a polar coordinate, and radial direction is denoted by rho. But this is not the density matrix, but the radial coordinate. And I have a size. I have a sphere whose size is R, capital R. So this is my region A. And the boundary of the region A is sigma. Sigma is a sphere. So this is the flat space, R to B. So but to compute the entanglement entropy or the Partian function, so we have to compute the first integral on the singular space Mn. So what is Mn in this case? So I have T rho plane here. So rho is the radial coordinate. And as you saw that to consider this space, you have to go around sigma n times. So this is T and rho plane. And here at rho equal to capital R, you have sigma. So Mn is taking the cycle tau, and the period of tau is now not 2 pi but 2 pi times n. Okay. So tau parameterizes this direction, this coordinate, around this point. And but here you have 2 pi n periodicity in this direction. So this is the Mn, and this is not easy to imagine. So I'd like to use the conformal mapping to make it clear. Okay, so now here I always consider conformal field theory. So I can use conformal mapping. Conformal mapping. So I originally had a class space whose metric is given by pt squared plus 0 squared plus rho squared times a metric of sphere, d minus 2-dimensional sphere. But I changed the coordinate, so I redefine p in this way. But yeah, this is not so important, but you have some coordinate transformation, and I introduce new coordinates tau and theta. So I have new coordinate. So after coordinate transformation, so you have some factor, some function of tau and theta here, tau and theta, and you have a metric for sphere. So you have sine squared, theta squared, cosine squared, theta, and the metric for d minus 2-dimensional sphere. Okay? So this part describes the d-dimensional sphere. Okay, I started with the class space, but after the mapping, I have a sphere, and if theory is conformal, then you can ignore this factor, and the Partition function on the original space is equal to the Partition function on this sphere, and the sphere is much easier to understand. So here, my sphere has a period range here. So this is the tau circle. This is tau, and this means d minus 2-dimensional sphere. But here, so we have sine theta in front of d tau squared. So tau circle shrinks at theta equal to 0. And similarly, so this sphere also shrinks at theta equal to pi half. Okay? So you have not the 2 circles, but yeah, you have 1 circle and 1 sphere, and 5 are over theta. But okay, so we want to consider the Partition function on Mn, not flat space. So usually the period of tau is equal to 2 pi, but we have to multiply n to get the covering space, Mn. Okay. Well, this is very easy because you just change the period of tau circle. You multiply n here. This is pretty easy. And I will call this manifold or this sphere as a n covering sphere. I will denote it by SD with n. And I change the symbol to make it distinguish from the lineage V. Okay, in the end, so what we get is that I will finish in a moment.
That's why I didn't take try anyway. So.
Okay, in odd-dimensional CFT, but we have odd-dimensional. So for CFT, the Partition function Zn this is the Prussian function on the n-covariant space Mn, but this is equal to the Prussian function Z on that sphere. I will call it the n-covariance B sphere. N-covariant B sphere. Okay, so after the mapping, the reigning entropy across a sphere is given by the Prussian function on sphere, n-covariant sphere. So this is a reigning entropy, but instead of having a Prussian function of the original space, we have sphere Prussian function, but we have n-covariant space. This is the final result. Okay, I replace the Prussian function Zn with the Prussian function on the n-covariant D sphere here after the mapping. But here I focus on only the entanglement entropy across a sphere. So it holds only for a sphere, spherical entanglement surface. So if you scatter a sphere, then you cannot get such a representation. Okay. And after taking n goes to 1 limit, we have very interesting relation between the entanglement entropy and the sphere Prussian function. So here we have a sphere Prussian function. Okay. We have sphere Prussian function here, and also n-covariant sphere Prussian function here. And after taking n goes to 1 limit, so what we get is that the entanglement entropy of across a sphere is equal to log of the Prussian function on around the sphere. Okay, I take n goes to 1 limit here, and I expand the Prussian function on the n-covariant space. If we expand this Prussian function around n equal to 1, it should start with log of the Prussian function on sphere, usual sphere. But here, at the subleading term, we can regard this Prussian function as a deformation from the round sphere. So I describe this metric by a change of the metric, and it should be in this form. I have a variation of the metric which describes the deformation of the sphere, but this should be proportional to n minus 1. Okay, and here we have expectation value of the stress tensor, but for CFT, it should be 0. So it starts with all the n minus 1 squared. Okay. So this guy doesn't contribute in n goes to 1 limit. So that's why we get this form. Okay. So, but this was derived by Cassini, Myers. Okay, so I will use this relation in my second talk on Friday. But I'd like to finish my talk today here at this point. Thank you.
Any burning questions?